Let's now move toward a more general description of diffraction in a crystal. Previously, we discussed the Bragg law and the law condition from a geometric point of view. Now we want to derive the diffraction condition starting from a wave scattering perspective, in which we treat the crystal as having a continuous electron density distribution. The geometry of the scattering process is illustrated in the figure on this slide. The source point of the incident wave is assumed to be very far away from the crystal. The incident wave travels toward the crystal with a wave vector k, and we observe the scattered radiation at a detector located at position R, measured from the origin O. Because the detector is placed far away from the crystal, we call this the far field region. And recall that the X-ray beam is formed by passing the X-rays from the X-ray tube through a pinhole on a lit screen. At positions very close to the pinhole, the wavefront is spherical. At a distance far away from the pinhole, the wave may be treated as a uniform plane wave, as shown. So consider an incident plane wave arriving at the crystal. The instantaneous electric field of the incoming wave at the small volume dV prime at R prime can be written in this expression, where the subscript I stands for incident. The bold-faced E naught denotes the complex field amplitude vector. E to the I k dot R prime minus R sub s is the standard plane wave propagation factor, and the time dependence is e to the minus I omega t. Please note that the instantaneous electric field is written in bold calligraphic font, as shown, because it depends on position and time. Also, in this expression, the source position appears as a constant phase offset, while the spatial dependence at the differential volume element dV prime right here is the usual plane wave factor, e to the I k dot R prime minus R sub s. Now consider the crystal. Instead of thinking of atoms individually at this stage, we examine the scattered field from a small volume element dV prime located at the position vector R prime from the origin O. When the incident wave reaches this small region, the electrons there will oscillate and act as secondary radiation sources. In other words, each small volume element scatters the incoming wave in all directions. Now, if an X-ray detector is placed at the position R, right here, which serves as the observation point, then the direction of interest is the direction from dV prime to the observation point. So our goal is to calculate the total electric field observed at the detector, which results from the superposition of waves scattered from every small volume element in the crystal. So this is the starting point for a wave-based description of diffraction. Next, we consider the wave scattered by one small volume element, dV prime, located at position R prime. When the incident wave reaches this small volume element, it induces oscillations of the electrons within this region. These oscillating charges then radiate electromagnetic waves. The scattered wave emitted from this small volume propagates outward as a spherical wave, which takes the form of e to the I k prime dot capital R divided by capital R, where capital R equals R minus R prime. As shown in this figure, it is the vector connecting the scattering small volume element dV prime to the observation point. So at an observation point located at position R, the scattered field from the volume element dV prime can be written approximately as shown in this expression. So it is proportional to the incident field at position R prime, and it takes the form of a spherical wave. Next, we make a physically reasonable assumption, which is the amplitude of the scattered wave is proportional to the local electron density or charge density from which it is emitted. So we introduce the electron density n of R prime. This means the scattered field from the small region becomes proportional to the electron density at position R prime, the incident electric field also at this position, and the phase factor into the ik prime dot capital R divided by R, as shown in this expression. Now we also apply an approximation appropriate for diffraction experiments. The distance R from the differential volume dV prime to the observation point is given by the law of cosines for the triangle formed by lowercase r, R prime, and capital R. After rewriting the expression shown here, taking the square root of both sides and applying the binomial approximation for cases where R prime divided by R much less than 1, the distance R can be approximated as lowercase r minus R prime times cosine theta, where theta is the angle between R and R prime. Please note that the condition R prime divided by R much less than 1 suggests the detector or the observation point is very far away from the crystal. So this is known as the far field approximation, and when such an approximation holds, the vectors capital R and lowercase r are effectively parallel to each other. This approximation greatly simplifies the mathematics and allows us to express the scattered wave in terms of simple phase factors. Since the scattered wave vector k prime is in the direction of the vector capital R, the scattered field at the observation point scattered from the small volume element dV prime can then be written as shown in this equation, where k prime dot capital R is simply the product of the magnitudes of k prime and the vector R. Replacing capital R with R minus R prime cosine theta, expressing k prime R prime cosine theta in its inner product form, which is k prime dot R prime, and inserting the expression for the incident plane wave at R prime, we end up with this expression. So this is the scattered field at the position R contributed by a small volume element dV prime located at R prime within a crystal in the far field approximation. Please note that each volume element contributes a scattered wave at the detector or observation point with a specific phase, as the distance between each differential volume dV prime and the detector, as well as the wave vector k prime toward the detector, depend on the position of a differential volume. So to obtain the total scattered field observed at the detector, we must sum the contributions from all small volume elements within the crystal by integrating the differential scattered field over the crystal, as expressed in this expression. It is worth mentioning that although the scattered wave vector k prime changes its direction towards the detector when originating from different differential volumes, the scattered wave vector k prime is essentially, or in practice, the same for all points in the sample, given that the detector is far away from the sample crystal. So the total amplitude of the scattered field in the direction of k prime is therefore proportional to the integral of n of r prime multiplied by the phase factor e to the I k minus k prime dot r prime over the whole crystal. This integral is called the scattering amplitude and is typically denoted by capital F. It contains all the information about how the electron density distribution inside the crystal affects the diffraction pattern. So one of the most important insights in solid-state physics emerges here. This integral is mathematically a Fourier transform of the electron density distribution. Therefore, the diffraction pattern we observe experimentally is directly related to the Fourier components of the crystal's electron density. In other words, diffraction experiments measure the reciprocal space structure of a crystal. This result explains why the reciprocal lattice plays such a fundamental role in crystallography and solid-state physics. In the next step of the derivation, we will see that strong diffraction occurs only when k prime minus k equals a reciprocal lattice vector, which is precisely the law of diffraction condition. Up to this point, we have derived the scattering amplitude. Now we ask an important experimental question. What do we actually measure in an X-ray diffraction experiment? In most cases, we do not directly measure the electric field itself, and we usually do not measure the complex scattering amplitude F directly. What we measure is the intensity of the scattered X-ray. Therefore, the observable quantity is the intensity that is proportional to the square of the magnitude of the scattering amplitude, as shown in this expression. Now, if we define the scattering vector as delta k equals k prime minus k, which is the change in wave vector caused by scattering, then the phase factor e to the I k minus k prime dot r prime can be rewritten as e to the minus I delta k dot r prime. We end up with the expression shown here. This is a very important equation. It tells us that the measured diffraction intensity is the square of the magnitude of the Fourier transform of the electron density. So experimentally, diffraction gives us access not to the electron density directly in real space, but to its Fourier components in reciprocal space. The figure shown here, adapted from Professor Kittel's book, is just another version of the schematic diagram in Professor Ashcroft's book that we discussed earlier. So I'm confident that no further explanation is required. So this slide establishes a key connection. The electron density determines the scattering amplitude. The scattering amplitude determines the intensity, and the measured intensity therefore carries information about the reciprocal lattice of a crystal structure.